So, quick question. How much of quantum mechanics you have had? Oh, so whatever quantum mechanics you know, you just know up here. Okay, excellent. That actually makes it easy. Right. And you're all second year BSc students. Is that? No, first year completed, right? So you're like almost practically second year, huh? Yeah. So I will consider it as a first year done. So it's like second year. Right. So. Right. So what I will be doing is 5 lectures on quantum entanglement. So any idea about quantum entanglement? Huh? Have you heard of it? Oh, you have? Who has heard it? You? Okay. So what do you know about quantum entanglement?
Only some preliminary idea about something like that. So you can
No, let him finish. Yeah, let's.
basic relationship of between matter and antimatter. If it's about so if both the matter and antimatter is located at a distance of.
Fine. So it's weird, right? Something very weird. Excellent. So what do you know about quantum entanglement?
Heard it in the context of quantum computing.
Uh-huh. That's it? Slightly practical. Okay. Anybody else? Any idea? Quantum entanglement? Yeah, you have some idea? Yeah, so.
Somebody told me that two different particles very far apart, their states can be connected so that if you measure the state of one, you can immediately know the state of other particles.
Right, slightly more precise. So I think everybody is correct. This quantum entanglement is philosophical, practical, weird. So it has all the components. But one thing is very clear, that nobody understands it properly. So that makes it a very nice situation, that, I mean, if you think that I don't know anything, I can always say nobody knows. So, right. So, okay, so let me just give you the how I have planned it. But this entire plan, since you don't have you haven't had any quantum mechanics, I will be using almost no math. I have talked with Professor H.C. Verma, and he said you have to make it a popular level. So I'll try to make it very popular, so that at the end of 5 lectures, you should think this area of research is very exciting, at least. Even if you don't understand anything, but you just should feel that, you know, just exciting. So that is my only aim. So again, feel free to ask questions. I am going to make this at a very conceptual level. So I just want to be able to convey the basic ideas, the basic philosophy about quantum mechanics and quantum entanglement in particular. So just ask as many questions. This is not a proper course, so there's no grade. So I'm not tensed, you're not tensed. So just ask as many questions as you like. Right. So this is the broad subject for the next 5 lectures, and what I'm going to cover in this is like quantum superposition. Any idea? Anybody? Huh? Any idea of quantum superposition? No. Excellent. Quantum uncertainty. Then we will do EPR paradox. Any idea EPR paradox? Anybody heard of it? Podolsky-Rosen. Excellent. Right. What else I have on my list? Bell's inequality. Any idea about Bayes inequality? Anybody? Something like that. Yeah, that's enough. Then what else I have? Hidden variable interpretation of quantum mechanics. Any idea here? This I think nobody has any idea about. Hidden variable interpretation of quantum mechanics. Oh, yes, so that much information. Yeah, that's absolutely correct information. And then we'll do finally some application. And well, I'll try to cover a few quantum computation. Somebody just mentioned. Or let me say quantum information computation comes as part of that. Then there's something called quantum cryptography. Then something called quantum teleportation. And something called quantum metrology. Okay. So, well, ideally, these would be the topics of PhD level elective course, but we'll try to do it at the second year level. I still consider you as the second year because you're done with first. Okay. So, yeah, so we'll try to skip all the math, and my aim would be to actually convey the basic physics and the basic ideas about quantum in general, and as applied to these principles in particular, and just try to convince you after 5 lectures that this is an exciting area of research, both philosophically and practically. So, these have this area has the foundational questions as well, plus you can work on next generation technology, right? These will all lead to next generation technology using the concepts of quantum mechanics. So, by the way, my font size is okay, right? Can you see it? Or should I write bigger? Is that fine? Okay. Right. So, yeah, so what was done in the last 2 lectures? Can you just tell me the topics, what Amit has done just now? Huh? Schrodinger's equation and wave function, Schrodinger, okay, and that's it? Huh? Basic concept, okay. So, what is a wave function? Huh? No, you have to slightly louder, yes. Some function of position and time. Can you be more precise than that? Can anybody be more precise than that? Some function of position? Some representing the state of the particle, okay. Anything else? Yeah, wave function is just a mathematical concept. It is not a physical object. So, if you're not being precise, it's not your fault because it is not precise, and nobody knows. So, at that point, let me just quote this, and this makes me very safe. This is one is from Einstein and one is from Feynman. People know Einstein and Feynman? Of course, everybody knows. So, I just write it down. This one is by Einstein. You may have seen it already. Well, I want to quote him exactly, so. Okay, so this one is from Einstein. The next one is from Feynman. This is much shorter. It's not as long. Right. So this is from Einstein in 50s. That all these 50 years of conscious brooding has brought me no nearer to the question, to the answer to the question, what are light quanta? And he's referring to quanta, basically referring to the quantum mechanics single particle. But nowadays, every Tom, Dick, Harry thinks he knows the answer, but he is mistaken. That means, as of 1950, Einstein doesn't think that the quantum mechanics is well understood. Now, this is in 80s. Feynman, it is safe to say no one really understands quantum mechanics. So Feynman in 80s, he thinks, not yet. 2016, it is still the situation. Okay, so we know more, but still nobody can say that we understand quantum mechanics. And the main thing, that wave function. What is a wave function? Nobody has a proper answer. It is just a mathematical object using which you can do the calculation. But physically, what it means, what is the physical reality behind that wave function? Nobody has the final concrete answer yet. Okay. So with this in mind, that means nobody really knows. I'll try to present whatever is kind of known to the community, the broad level. There may still be debate of how one presents one concept versus how the other one presents the same concept. And this is true when things are not yet settled down. So quantum mechanics, you may have somebody teaching one way, somebody teaching other way. But what I will do, again, will not go in too much into deep, but just overall, what are the concepts, how do we understand quantum mechanics. Okay. So with that, so any idea what is the difference between classical and quantum mechanics, whatever you know so far, 2 lectures? What is the difference between classical mechanics and quantum mechanics? Microscopic world versus macroscopic world. Okay. What else? Anything else? Something weird versus something concrete. Wave function doesn't make sense. Classical, XP makes more sense. Is that determinism, right? So determinism will be one very important point that let me just write down. So this is one very important difference between classical and quantum world, that in classical you try to have any set of equations by which you would be able to predict exactly what would be, after a while or after a distance. So that is a part of classical theory. Quantum, you just cannot do it. So you have some idea, oh, maybe it will be there with 50% probability, it will be there with 25% probability, it will be there with 33.3% probability. You can be very exact about the probability, but the probability is not exact. So determinism is a very important difference. What is the other thing? Well, I'm not expecting you to come up with everything, but anything else? Superposition principle. Anybody has heard of it? Superposition principle. In what context? Yesterday you were doing, right, in optics lab, so I saw it. So superposition principle. So whatever you know about superposition principle, I'll convince you that it is wrong. So superposition principle, of course, is different in classical world than in quantum world. What else? What else? Well, one more point. I mean, I have few more points, but one more point I expect. So what else? Equation of motion. You are dealing with Schrodinger equation you have never heard of, right? So why a new equation? So the equation of motions are certainly different, and why they are different, this we will get to. So I mean, you're familiar with Newton's equation, everybody, Maxwell's equation, but was that not enough? I mean, Schrodinger equation. So of course, in the quantum world, you need a new equation to describe things, and that is the Schrodinger equation. Anybody's question? Okay. What else? Yes. So yeah. So that, let's say I'll put in part of the equation of motion, that yes, things here, when we write the equation, it is in terms of wave function, which is not very well defined. In Newton's case, it is in terms of position momentum, which you can actually visualize, oh, something is being here or something is moving with that speed, kind of. But wave function, no idea, right? So there are a few, one thing I'll just add here is something called wave particle duality. Any idea what is wave particle duality? So can you be louder? A particle behaves both as a wave and a particle. Well, a particle cannot behave as a wave. Particle is a particle, wave is a wave. But a system can be particle and wave at the same time, and that precisely is what wave particle duality is. So this is, I would say, this is the, as people say, quintessential feature of quantum mechanics, is wave particle duality. We understand particle as being what? Something, it is characterized by position, that it is somewhere, right? It's a localized somewhere quantity. What is wave? So it is everywhere, right? So something can be everywhere, something can be somewhere at the same time. Can that be possible? Maybe. What do you think? Can there be a system? Well, I won't call it particle. So can there be something, a system that is everywhere and just somewhere at the same time? No. You have to answer in yes or no. Can you have a system which can be everywhere and somewhere at the same time? Yes? Who is yes? Who are yes? Yes. No? So slightly more no than yes, but more or less neutral votes here. Oh, so he's putting a complaint that this is not a valid question, right? We need to put a measurement, you can actually put it at the same time. But, huh?
Nobody can answer the question.
Oh, I can.
Yesterday only we saw that Einstein said that this will be like something three people said the second answer was like this answer can't be answered.
No, no, but this question we can certainly answer yes. And the answer is yes. You can, whether it makes sense or not, but the answer is yes. That you can have systems that can be everywhere and somewhere at the same time. I'm not doing measurement yet. So if I'm not doing measurement, then a system can certainly be everywhere and somewhere at the same time. Does it make sense? No, but the answer is yes. Okay, so who is convinced, because that is what my laptop is there to convince you. Well, not a laptop, but what I have on the laptop. So who thinks that this statement can be true? That somewhere and it's true? Oh, believer, excellent. And who thinks this makes no sense? You certainly think it doesn't make sense, right?
No, I think it makes sense, but I was trying to explain that.
Oh, going further. Okay, so we'll come to the measurement point. And coming to the talking of the measurement, so this certainly the effect of measurement. I mean, I will not actually go into it, but I would say these are the distinct features of quantum mechanics. This measurement is a very different idea in quantum mechanics, that as he is pointing out, if you make a measurement versus when you don't make a measurement, things are very different. Okay? In classical world, I mean, whether you make a measurement or not, I mean, you can actually predict it. But here, if you make a measurement versus if you don't make a measurement, I mean, things can be different. So, in fact, this was a situation. So, I mean, this is the same thing. If something is everywhere, but if you make a measurement, you find it somewhere. So, something which was everywhere suddenly comes to one point. So, was it already there and I happened to just find it there? So, these are all the questions that simply we don't know how to properly answer. This is mathematically, this is what we see in the theory, but we don't know how to properly answer it. And so, this led Einstein to actually say that, well, if I'm not looking at the moon, is the moon there or it's not there? Right? Is my looking at moon making it present or be there, or am I making it just be in that position that it is, or it's just, I mean, ideally it should be independent. Whether I look at the moon or not, if moon should be there, it should be there, right? But in quantum mechanics, things are different. When you make a measurement, that actually, well, you're making a measurement is actually part of the system that makes the system, and so things are different. So again, this part is, well, this leads to what's called measurement problem in quantum mechanics, one of the foundational problem. But I will mostly be focusing on this wave-particle duality, superposition principles, and little bit of determinism. Well, determinism is part of it anyway. Okay. Any question? No math yet. Please note. Right. So these are the basic ideas, and then today I'm going to actually focus on the superposition principle. But before we do that, we'll use we need a system, and that system is basically light. So we will start with the question as to what is light, and what these two quotes are also relevant to this question as to what is light. And then if you can see, he's actually referring to light as quanta and saying, well, nobody knows it properly, and that is, I would say, that is the case. Okay. Okay, so let's start with actually what is light. So any idea what is light? Huh? Well, light, certainly everybody knows something, right? So what is oh, so let me just make it more precise. Is light a wave or a particle? Oh, you could guess the answer, right? So now you're saying that being everywhere and somewhere makes sense? Yeah. So you have changed your mind. Excellent. Huh.
And if you are doing complex or something like that, then photoelectric effect and
So I mean, you change your mind quite so often, right? Sometimes the wave, sometimes it's.
that is Schrodinger's cat's thingy comes. That
I see. I see. I see. So yeah, so this is the confusing situation now, but back in 17th century, if you go, this question as to, if you go to 1700, people would say light is a particle. And what do you need? You need Newton's equation. That's it. Okay. Now, when you come to 1800, light suddenly became wave. So people will say light is a wave. So, and what do you need? You need Maxwell's equation, you need Young's double slit. So I will not put Young here, but I mean, starting from Young, light was being considered a wave. So all you need is Maxwell's equation, light is a wave. Okay. But 1900, confusing situation. Light is a particle. As well as, and now what do I need? I need the longer Schrodinger equation. Okay. So this is just the broad overview as to how people kind of thought, and this understanding is still intact. We don't have we don't have better understanding than this. So what do I mean when we say that light is a wave? What is a particle? Sorry, what is a wave? I mean, this is very basic. I mean, everybody knows the answer, right? So what is a wave? Huh? Function? Function of space and time carrying energy. Okay, slightly mathematical, that's okay. So for me, wave is this. That's wave. As simple as that. Or, well, let's see if I can draw it. So it's a very, what is this? Thank you. So like so water waves, right? So the water waves or waves on a string. So that's wave. What's particle? Well, we said we'll not use too much math. So sorry. I mean, so yeah, excellent. So that's my particle, right? So and if you have, let's say, a screen or your camera, like this camera is basically has a detector which is basically two-dimensional detector. So if you have two-dimensional detector and if you have particle coming in, you will see a lot of dots. That means these are measuring the presence of particle. So this is how we understand particle. This is how we understand wave. Both we can very physically see it. If I say wave, I am thinking in terms of water waves, or when I do a string like that, there's something on the string, that is my wave. When I'm thinking particle, I'm thinking something just like that, something being somewhere, not moving. Well, it can move, but even if it moves, I know precisely where it is at what time. Okay. So, and now in a while we'll see that these two can coexist, but we'll see how. Okay. So now we want to just look at the superposition principle in the context of wave and in the context of particle. I think everybody is familiar with superposition principle in the context of waves, right? That's what precisely you did yesterday. So what is superposition principle in the context of wave? Well, this everybody knows the answer, but let me ask it anyway. So let's say I have let's see if I can draw it. So this is an old style bulb. So that's my source of light, and suppose this is, I mean, my understanding of light is as waves. Then what I do is put a slit like this, and there's a screen over here. So what will I see on the screen? Huh? Diffraction. Okay. So like, what is diffraction? Huh? Loud. Who sets up? Fringes. Oh, you're slightly advanced. Huh? Bending of light. Spread out. Yeah. So I mean, we are not that mathematical yet. So we'll say, okay, yeah, some spreading out. Something like that, right? There will be some structure here and there, but we are not that advanced yet. So it's just that some scattering, some broadening, some because of bending and diffraction. Okay. So this is how we understand diffraction. Now let's say if I open up the second slit over here, then what happens? And let's say if I close it for now. Well, let's have it open. Yeah, so let's say if I open the second one, then what happens? I mean, suppose only this is open right now. This gives me this. If I open a new one and kind of close it, then what happens? New thing, right? Just a tiny bit shifted, right? And now if I open up both, yes. So, well, let me, since this is so important. So if you have both the slits open, then this big envelope will certainly still be there. But inside this big envelope, you will see this fantastic fringes. Right? And this is what we understand by classical superposition of waves. Now, I haven't done any math. This is what precisely you see. But how do you explain this fringe pattern? Huh? What do you mean by two waves superpose? No, superposition is the right word, but what do you, can you be more precise, more mathematical or more physical, whatever? Huh? Displacement can add up. Amplitude, so here you have some amplitude, you representing waves by some amplitude, you divide that amplitude and then you add it up, right? So this is explained using superposition of amplitude, right? So that is the main thing. Or rather, I would say first the division of amplitude. So something was coming in, and I would say that, okay, whatever was coming in, part of that amplitude goes through this and part of that amplitude goes through this. So this is basically the division of amplitude. Okay. Now, is this when you divide this full amplitude in parts, are you dividing the energy of that total thing as well, or no? You are, right? So everybody agrees? Is there any disagreement? Huh? When you divide amplitude, are you dividing energy as well? Yes or no? Who is no? Let me see. You're no? And why? No. See, I'm saying, let's say I have 1 watt of energy coming to the slit, and let's say this is like some 10 centimeter, okay? 10 centimeter and you have 10 watts of energy coming in, and let's say this is like 1 millimeter. So will you have all the 10 watts going through the slits, or will you have only 1 watt going through the slit? Entire 10 watt?
Then only we get 20 watts intensity, right? Like if it's
No, no, hang on. I'm saying 10 watts was coming like that, okay? And this area is blocked. This area is blocked. Only this 1 millimeter area and this another 1 millimeter area is actually open. So if you have 10 watts of light coming in, how much will get through this slit? 10? Well, we can do it right away. We can test your theory. So I have the screen. Well, I don't have a very nice source. Well, you take this screen, cut a hole in it, and look through it. This tube light, right? Are you getting the entire as you were getting before, or slightly less? Right? So of course, no. Is it fine? So it will be what? 1 watt, 10 watt? 1. So 1 watt going through this, 1 watt going through this, right? So within classical description, division of amplitude basically means division of, or also means division of energy. But this is what I am going to prove it wrong, that this is actually wrong. So I will come back to you. But this is what the classical understanding of interference is, that this is how interference works. That we try to explain it through division of amplitude, whatever is coming in, we divide the amplitude and then add it up. And one essential part of that process is that division of amplitude also associated with division of energy. Nevertheless, this is how you do it, and so this is my classical superposition. Of waves, of course. Okay, any disagreement here, or you're fine? Let's see what else I have. Okay, so now what if I do the same experiment with particles? What will I expect? Any idea? So again, I have a bulb. It looks like the same bulb, but is actually different. In that, it's basically throwing out particles, whether you believe it or not. The other one was just throwing out waves. Now this one is throwing out particles. Now if I put a slit like this and have a screen over here, what will be the distribution on that screen? No, but I'm saying too many dots, like 1 million. So the distribution of dots, right? So what will be the distribution of dots? That's the question. High, something exactly similar like that, right? So all those dots, if I correct all these dots, it will be something like precisely the same, almost. And well, will I have this wiggles? Let's say we don't know, I mean, so let me not draw it. It's just some broadening. I don't know the mathematical function. And again, same deal. If I, let's say, close it and open up the new one, what will happen? It's tiny bit shifts, but it remains almost the same. Now, the question. So same source, but I do this. No mathematical equations yet, right? So now same source, I now open up both the slits. Then what happens? Two patterns will be side by side, and if I add them up, it will just be like one big heap kind of thing, right? Something like this? Everybody agrees? Okay. So this is question? Yeah, I mean, this is my drawing. I mean, it's not as accurate, but yes, something like this more or less will be like a heap. So yeah, so this is exactly correct. This is what happens when you send in particles. The particle either goes through this slit, either goes through this slit or that slit, but at the end of the day, at the end of the journey, it basically accumulates, and it's just the addition of those two. And this is how particles are supposed to behave. Right? Just make a heap, even if you're going through two holes. Don't do anything else. But when it's waves, if they are going to go through just one slit, they will give you a broadening and heap. But if you have two holes, they can give you something more interesting, and that is the interference pattern. Okay, but now let's say if this is the slightly different source. If I now, although I'm drawing it exactly in the same way, but this is a quantum source. Okay, it's a quantum source, so maybe it's just sending out particles. But one information I have is it is a quantum source. So what will be the pattern now if I have both the slits open? What time does this? This goes up to 11:50. This class, right? Okay, fine. So what will be the situation now? Let me be more precise. So let's look at the when we are doing particle, we have to look in terms of screen so that we can see the dots. So if we are here, we'll see more dots, so that I'm collecting, and maybe just a few here, right? More or less. I mean, this is just. So what will be the situation here? Is the same or something can be different? There can be something different. Huh? And why? Wave function predicts this. No, but I don't know any math. But so what do I do it without? Why? I mean, I have a particle, right? Somebody has told me it's a particle, and then I know that if it's a particle, it has to be somewhere. So that means if it encountered the two slits, it has to make a decision that whether it wants to go through this or go through that. If it goes through this, it goes through this and it hits here, right? Waves, we divided the amplitude. Part of the wave goes through this, part of the wave goes through this, and hence I can have interference. But here, can I say the part of the particle goes through this? No, I don't break the particle. Then what do I do? No, I don't know what we're supposed to see. So then what pattern you're supposed to see? Same thing, right? So C is predicting the same thing, even if it's a quantum particle, it should be the same thing. Anybody else? If you differ from her, you'll be right. So yeah, you are actually right. It will be actually interference pattern in that case. But how we can explain mathematically, physically, we don't know it yet. Believe it or not. Okay. And I actually am prepared to actually show you this actual thing hitting the screen one by one and then actually making the interference pattern. Hopefully, if the thing works, we'll show you. So any questions so far? It's very, Okay, so this I will show you through real experiments so that you have, since I'm not showing you math, I need to show something so that you can believe me. So the situation is that it is still it is still particles going into the setup one by one. So a particle basically has to make up its mind. So a particle the light is gone, isn't it? Goes through either slit number 1 or slit number 2. Okay. So because if we are saying it's a particle, I mean it has to, it's a dot, it's a point, and so it has to either go through this or through that, right? So it has no, and we have a proof here that a particle hits the screen at a localized point. Okay, this is the proof. Well, I'll show you a slightly better proof, but that's a proof on the screen. It hits it one by one through slits. It either goes through this or through that. So these 2 points are absolutely clear. If you're saying it's a particle, yet you have interference. What interferes? I don't know. How it interferes? Maybe that still I don't know, but it actually interferes. Okay. So again, the moment we say it's a particle, it's absolutely sure that the particle can only go through this or that. Also, when it hits a screen here, it has to hit it at the localized point, but yet we see interference in the distribution of particle. Okay. So this is the idea of quantum superposition. Now, sorry, this is what you see in quantum interference, quantum superposition. But like, how do you explain it? I can't divide the particle. That means I can't have division of amplitude. So what do I have? I cannot have division of amplitude in the usual classical sense. So, but if I'm seeing interference, how do I explain it? Huh? Yeah, but how do I explain it? Wave has, when we were doing wave amplitude, we could divide the amplitude and then add it up. But what do I do now? All I know, I have particle. Particles cannot be broken, and it goes to either this slit. The entire thing goes to either this slit or through that slit. So how do I? What do we divide? What do we add? You know the answer, right? Answer is as weird as wave function. We divide the wave function. What it means? Well, I don't know. We add the wave function of, we superpose the wave function afterwards. What it means? Well, maybe I still don't know. But nevertheless, it's the addition of or division of wave function. Okay, now coming back to u. Now this division of wave function, is it division of energy or it is not? When I divide a wave function, because I don't know what a wave function is properly physically, but when I divide a wave function, am I also dividing the energy associated with that wave function or not really? Yes, no? Yes, right? So you're absolutely correct. Yes. So this does not mean, and this does not mean division of energy. And this makes sense. Why? Because it's a particle. Particle I can't divide. So that means the entire particle has to go through this or through that. That means entire energy went through this or through that, and it's not the energy got divided. Okay. So division of wave function is not equal to division of energy, but this somehow is able to explain this interference pattern. I'll be more precise further, but this is the fundamental difference between classical superposition or classical interference and quantum superposition, quantum interference. So which one is correct? We have two ways of doing things. This is quantum, and this is classical. I mean, this everybody has done class 11, 12, first year at least, right? This you may not have done, but let's say you believe me for now. But this is one interpretation, one explanation for interference. That is another explanation of interference. But you want to have one theory, right? You don't want to have two different theories. So which one is correct? And this is as different as dividing the energy and not dividing the energy at all. So which one is correct? Any idea? Both are correct. No. Huh? Quantum has to be correct, right? Of course. So yes, so this quantum is correct. So this is the correct theory, but maybe it is actually needed only at very low light levels. Okay. What about this one? I can't say it's completely incorrect, because just yesterday you have verified it, right? So today, just within 24 hours, I just cannot say that this is incorrect. So this is fundamentally incorrect. Okay, but somehow it works at high light level. Okay, so this is fundamentally incorrect, but it works at high light level, and which is what we have verified just yesterday, that when you can see things, light, very nice interference pattern, perfectly absolutely clear. But when the light level goes down quite a bit, then this theory is actually not applicable at all. This theory is incorrect. Okay, because this theory, in a sense, says that something coming from this part of the wave and something coming from this part of the wave actually see each other and then interfere, right? And it was Dirac who actually pointed out that, of course, this is fundamentally incorrect. This is correct, and how do you explain it? So in terms of Dirac, a single photon interferes with itself. This is the explanation of this way of looking at things, because here I have one particle going either through this or through that, like one by one. So in this interferometer, I have only one particle at a time. So what is interfering with what? There it was clear, part of the wave interferes. But here if I have only one particle, so what interferes with what? What interferes, we said, is a wave function. The another way of saying that a single particle interferes with itself. Does it make sense? Maybe not, but that's what it is. And he even further said that the interference between two particles never ever happens. Two photons or two different particles, they never ever interfere, believe it or not. But this is actually true. Nobody has so far been able to actually disprove it. Now in the context of quantum entanglement, we have a system consisting of two particles. Even in that case, we don't see two particles interfering with themselves. It's like a two particle state interferes with itself. So I'll try to come back to that point and explain it slightly better. But it is a system. That system here, in this example, consists of one particle, and in quantum interference, that system interferes with itself. If the system consists of, let's say, 2 or n particles, that n particle system then will interfere with itself. It's not that the n minus 1th particle is interfering with n minus 2th particle or something. Okay, so this is quantum interference, and this is absolutely correct. Nobody has been able to yet point out any mistake in this one. Classical explanation, it works, but only at high light level and not at very low light level. And what would be the proof that this is fundamentally incorrect, that it works at high light level and not at low light level? What will be the proof? So now let's say if I have an interference pattern, and then if you turn down the light, what will happen? It will be the same interference pattern, but less intensity, right? Overall less intensity. If you decrease it further down, overall less intensity. Even further? So I mean, you can't think further, right? It will just be okay, lower intensity. But at every situation, you will expect an interference pattern, right? It is precisely classical explanation, of course. But this is not how it happens. And let's see if I can show that to you. 20 minutes. Okay. So oh, here, this one. No, you can actually measure the interference pattern. You don't believe me, right? I'll show you. I have it recorded in my lab. And if you don't believe, because I have recorded in my lab, because if you don't believe it, you can come and see it actually. So yeah, you can certainly record the interference pattern. I'll show you what I have recorded. Oh, excellent. So again, okay, so before we do that, let's say, so this is my Young's interference pattern. Not a very good quality because that has some other reason, but you can identify this as Young's double slit experiment, right? And so how do you do Young's double slit experiment? Let me quickly, you have done a more sophisticated version of it. This is my laser pointer. You can see that. Well, so I'll try to convince you that I have some few things. This is the cheapest Young's double slit interference. So what I have, well, not the coins, but this is a needle. I don't know if anybody can see it, but it's a 500 micron thick needle. And so why is this a double slit? Well, so see, this is a beam of light which has some size, about a millimeter or 2 millimeter. Now in this 2 millimeter thing, if I put a needle which blocks kind of part of it, then this is one slit, that's another slit. So this becomes the cheapest way of making a double slit, okay? And let's say hopefully it works. So see, I come here, I'm going to try this wall. Can anybody see any interference pattern? Probably not. Too much light here. Huh? If you come very close, can you just go and verify that I'm not lying? So actually you can actually see some interference, but wait, don't go close to the, yeah, you be on the left side, and now look at it. I don't want you to, can you see something at least? Yeah. Excellent, thank you. So stay there. So this is a needle which is slightly thicker. Now if I try, huh? Oh, somebody can donate a hair? So yeah, so hair is actually 50 micron. In that case, so this is a copper wire I have. This will be slightly bigger, hopefully. Can you see slightly bigger?
Yes, sir. Yes.
So if you can somebody donate a hair, I can. Yeah, found it. Okay. Whether you can see it or not, it's my hair, and this is about 50 micron. Well, I have measured it, so that's how I know. Well, it is much bigger, but I think the light is so intense here that I don't think I can see it. Can somebody see it? Okay. So, Bill, this is what you have seen, but all that I wanted to tell you that this is what you see in a classical Young's interference, okay, at highlight level. But now I want to go to a level where I want to make sure that I have photons coming one by one, okay. This Young's double slit, this interference, I want to make sure. So what is a photon? Huh? So how much energy? H nu, yeah, of course, excellent. So that much you know. So H nu or H bar omega is the energy. So if you can have a bulb that emits just H bar omega energy, then you can call that, okay, that's just a photon, and that a photon is going through slit one at a time, okay. So now you have to believe me on this, that I have set up an experiment where my source intensity is so low that it is basically one photon going in one by one and hitting the detector one by one, okay. So let's see. Not this one. Yeah, can you see it one by one? So this is real time. This is recorded real time. It's just. Can we turn off this light? Oh, there. Excellent. Well, those are not the fringes. Those are, I think, some ripples in the from that side if you're seeing something. So this is like one photons coming in one by one, right? So I don't think I have as much time. So this is a recorded movie, and this has been recorded for about 50 minutes, 47 minutes. So, but you're convinced it came in one by one, right? So at least I have, in fact, if you want, we can go back, see that single photon. You are seeing a single photon, believe it or not, okay? This is a single photon coming in one by one. And then if we now run the movie slightly faster, that's how it comes actually. And what is this? This is an interference pattern, right? This is an interference pattern consisting of all dots. But if you just integrate the intensity, you can certainly see precisely the same interference pattern, right? So this is single photon interference. Can I explain this using division of amplitude? Of course not. How do I explain it? Wave function. Does it make sense? No. Is it true? Yes. So the same setup, that's why I showed you the figure earlier. In the same setup, this is what, when I collect it for much longer. So I mean, I don't collect for much longer, I just increase the intensity. And this is the same interference pattern, same fringe width, but this is, I mean, if you, at that rate, you will have to wait for days to get up to this intensity. But if you do wait, you do get this intensity back, okay? Okay, so I can have lights on. Any questions here? Okay, so now actually I have told you what we mean by single photon interference, and it is essentially that yes, you have particle coming in one by one, hitting the detector one by one, but yet you see interference, okay? And how do we explain that interference? It is through division of amplitude, which does not incorporate, which does not mean division of energy. So then how do you do it? Then you go back to Dirac and you say, oh, a photon interferes with itself. Interference of two different photons never happens. That's the best explanation we have so far, yes. I have just showed you, you can't. The entire thing goes through one slit and hits it one by one. Okay, so the resolution time that I have is, I think, like 0.2 second in that video, and in that 0.2 second I have just a single photon coming in the system. The intensity of my source is so low. Okay, so one by one. That's why I showed you like one by one, but yet you are able to build the interference pattern. Okay. Any other question? Okay, so right. So at least I have been able to convince you that this explanation of division of amplitude, this you simply cannot explain. No, not this, the other one. This you simply cannot explain classically, right? Because here things are coming in one by one. Here things are coming in one by one, and this is not just the overall reduced intensity, right? The classical one was, it was a continuous pattern, just the overall intensity becomes reduced. But here you actually have the dotted pattern. That is not part of the division of amplitude theory. So this is just a quantum. But again, as we say, if we if we just increase the intensity, then it becomes a very continuous intensity distribution. And for that, you don't necessarily need division of wave function. Even the division of amplitude is good enough. Okay. Right, so still no math, right? So I'll, what do I do now? Well, so I have one more. So this kind of superposition is familiar. Young's double slit is almost to everybody, but is this the only kind of interference we can have? So is this the only kind of interference you can have, or are there other types of interference. Well, I'm trying to make it this area slightly popular, so I'll show you something which looks very interesting. So far what we have been actually doing is that looking at the particles, the position of a particle and the momentum of a particle, right? I don't know if you, when in a Young's double slit, I'm putting two slits, I'm specifying the position of this particle at some plane. That okay, particle is here or here. It's about the position of the particle. Anything you do with the position of particle shows up in the momentum distribution of the particle. Okay, is this thing clear? Uncertainty principle. So, well, you can just take it from me right now that this thing, the interference pattern you actually see, is actually the momentum distribution of a particle. Okay, so if a particle is constrained to have just two positions, then right at this right here, the moment you constrain it, its momentum distribution is this, believe it or not. Its momentum, that means it will have some missing momentum, some momentum higher, some momentum lower. But of course, we don't have a detector here to actually measure the momentum. We go to the far field some distance, and then whatever you see as the position probability intensity distribution, that actually is the momentum distribution of a particle. Okay, just take it from me for now, but this will become part of the any quantum course very soon. Right, so this is about the position momentum. Last 20-30 years, people have been working with what's known as orbital angular momentum and angular position. These are again just two variables very similar to position and momentum. You have position, similarly you can have angular position. When I say angular position, what do I mean? I mean, if I draw a circle, that's the theta, that's the angular position of something, and it can have a width that will be delta theta. So angular position, uncertainty, angular position, that's how we understand. And there's some concept called orbital angular momentum. I mean, I'll not go too much into it, but it's just so interesting that I can't not show it. So, well, I'll show you some. So this is the way to look at orbital angular momentum. I mean, I will just quickly introduce it. So again, believe it or not, this is a laser, and when I hit this laser, you see a dot there, right? The circular dot. That is more like what I have over here. This beam has no orbital angular momentum, but I can have a laser source, I can have a laser beam that has a hole in it, and these kind of beams can actually carry orbital angular momentum. What do I mean? That for every h bar omega energy, you will have h bar L, where L is a number, integer. Okay, you can have h bar L amount of angular momentum, orbital angular momentum. And what do we understand by orbital angular momentum? Something that makes something rotate, right? So in fact, if I have intense light, well, it won't work with my hand, but if I have tiny bacteria, tiny bead, and enough light, it can actually start rotating. Again, believe it or not, but that actually is true. So I can have this kind of light beam is bigger and bigger hole. That means and they can carry bigger orbital angular momentum per photon. I mean, any beam having hole doesn't mean that it has orbital angular momentum, but this is one example of these. This is called donut beams that can actually carry orbital angular momentum. That means h bar L, where L is an integer, amount of orbital angular momentum per photon. That means per h bar omega energy. So why am I doing this? Because I want to do something interesting. So suppose I have a beam with L equal to 4. Okay, so it will have this kind of shape. How do I produce it? Just believe that I can produce it. So I have a beam which is of this shape, L equal to 4. Let's say I produce another beam which is L equal to minus 4. Intensity wise, they will look exactly the same. What will be the difference? If you actually look at the phase profile of these beams, the phase of an L beam, this is like 0, and that white is 2 pi, so it goes like 0 to 2 pi. And if L equal to 1, for L equal to 2, 0 to 2 pi, 0 to pi twice, L equal to 4, 0 to pi, 0 to pi, 0 to pi, 0, 4 times. If it's an L equal to minus 4, then it actually goes the other way. So that's the only difference between L equal to 4 and L equal to minus 4. One goes one way, the other one goes the other way. But if you look at the intensity, they are exactly the same. There's no difference. But what if you add these two beams? Well, one hint that I should give you, that this beam is actually represented by e to the IL phi. That means an L beam is being represented by the amplitude I am writing, or the wave function. If I write tiny bit of math, it will be e to the I, so something else which I am not interested in, e to the IL phi. That is, if I go like this will have this kind of a functional form, and e to the minus will be e to the minus IL phi. So, and where L is equal to 4, this is what I am working. L equal to 4 e to the IL phi, and L equal to minus 4 e to the minus IL phi. So, what will be the intensity pattern of such beam? All classical, nothing. Can somebody do the math? When you add the amplitudes, you add the amplitudes, right? And so, if this is how we represent amplitude, this is how we represent amplitude. What will be the total amplitude? Huh? Yeah, A factor is common. Sorry, yes. Oh, that was making it difficult. Sorry. Yes, A factor is common. Huh? Twice? Twice cos? Twice cos? L phi? L phi? Sure. Is it 2 L phi or just L phi? L phi, okay. So, what is this? It's a cosine function, means it's an interference pattern, and that is precisely what you see there. Okay. So, if I add these two beams, actually what I will get is this. Well, if I add if I am able to add the amplitudes of these two beams, then I get this as the interference pattern. Very nice interference pattern, right? But this I have obtained just by adding this and that. Just like in Young's double slit, we add the amplitudes of whatever coming through this, like the huge heap, the other one through this, and then when we add, we get an interference like this. Similarly, if we add a donut mode like that, what we can get is like this. What happens if you do it at the single photon level? Same? Okay, let's see. So, single photon is actually interesting because now it's a single photon carrying integer amount of orbital angular momentum. So, what if I have a detector there? So, I have a single photon with fixed energy, of course, h bar omega energy, and with fixed orbital angular momentum hitting my screen one by one, and then I am interested to see if it can actually make the interference pattern. Why it's interesting? Because I have either a photon with L equal to 4 or a photon with L equal to minus 4, and the question is, can it actually produce that pattern? So, let's see. So, again, to show you, if I do it at high light level, this is the real experimental data, you can actually see something like this. So, if you can add it, you can actually see something like this. Now, I will show you that if you make this system and then again measure it one by one, so do you see it's one by one? This is really recorded. Again, this is again for 15 minutes, and we can run it faster, and then you see that? You convinced now? That's the same pattern. Right? So, this is precisely the same pattern. Well, if I one petal here, 2, 3, 4, 5, 6, 7, 8, for L equal to plus minus 4, I have this 8 petal, and this is precisely, and if you again wait for long enough, this is what you see. And again, at that rate, you probably have to wait for days to actually get to this pattern. Okay. Excellent timing. So, any question? Actually, I'm done. So, this is about this is how we understand superposition principle in quantum mechanics, where the best explanation is that a photon interferes with itself, and interference between two photons that never ever happens. How do you explain it? Using wave function, division of wave function. Division of wave function does not mean division of energy. The energy, entire energy goes through either one way. In case of slit, this is one slit, or in case of Mach-Zehnder uniform, it's like one arm. So, entire energy goes through one way or the other way, but it still gives you interference. Okay. All right. Thank you so much.